are the solutions to question number 7 from the 2015 examination paper. 7a, we have a linear transformation from three-dimensional polynomials to vectors of dimension 4. We want to determine t of this polynomial and give an example of a non-zero vector in the kernel of t. And then we want to determine bases for the kernel and the image of t. Now for part B, it's a proof. If A is an n by n matrix and has an eigenvalue lambda with corresponding eigenvector x, then you want to prove that x is an eigenvector of a to the k corresponding to the eigenvalue lambda to the k. Okay, so for 7 part A, here is our linear transformation. So we want to determine t of 4 plus 3x minus 2x squared plus 3x cubed. So here you can see that a0 is equal to 4, a1 is 3, a2 is minus 2, and a3 is 3. So if we simply substitute those values, then we'll see that a0 is 4. So that's the first element here, 4. The second element is always 0. The third element is a2 plus a3, so that's minus 2 plus 3, which gives us 1, and the fourth element is 0. Now we want to determine a non-zero vector in the kernel, so we need the a0 to be 0, and we need a2 to equal minus a3 here. a2 has to equal minus a3. So a0 is 0. A1 can be anything, so in this case we just take a1 is 1, so we have x. And then the important thing here is a2 should equal minus a3, which you can see is true. So t of this vector gives us the 0 vector, so therefore x minus 2x squared plus 2x cubed is certainly in the kernel of t, because t of this vector maps to 0. For the second part, we want to determine bases of the kernel and the image. So we're going to concentrate on the image first of all. So here's our linear transformation. So you can see this vector here is spanned by two vectors. It's spanned by the vector 1, 0, 0, 0 to give you a0. And then the only other vector is 0, 0, 1, 0, because we have a2 times this vector plus a3 times this vector. So we just repeat this vector. So these two vectors span the image. They span the image. Now, obviously, these two vectors are linearly independent because a times 1 plus b times the other equals 0. The only solution to that is a equals b equals 0. So therefore, this is the basis for the image, and the dimension of the image over the reals is equal to 2 because we have two vectors. Remember, these angled brackets mean a spanning set, and the curly braces that represent the basis. So that's the set. Okay, for the kernel, we want to know when is this element here equal to 0. So this is equal to 0 when a0 is 0, but also when a2 is minus a3, which means that the general form of the polynomial p of x is a1x plus a2x squared minus a2x cubed, because remember a3 is minus a2 and a0 has to equal 0. Now this polynomial here is spanned by two polynomials. The first one is x, and the second one is x squared minus x cubed. And obviously, again, these two vectors are linearly independent. So straight away here, I've said that these two vectors form a basis for the kernel. So therefore, the dimension of the kernel over the reals, again, in this case, is equal to 2. Finally, for part B, we've got proof. So if A is an n by n matrix with eigenvalue lambda, then we know that the corresponding eigenvector satisfies this equation. So Ax is equal to lambda x. Now we can prove this by principle of mathematical induction. So obviously this is true for n equals 1. Ax, a to the 1x equals lambda to the 1x. Now we assume it's true for n is k. We assume it's true for n equals k. So a to the k minus 1x plus lambda to the k minus 1x so we assume that's true. And then we want to prove it's, sorry, this should say assume it's true for n equals k minus 1. Okay, so we do that, and then we multiply both sides by lambda. So we have lambda a to the k minus 1 x, and that's equal to a to the k minus 1 times lambda times x. Okay, but here we know that, remember that ax equals lambda x. So lambda x is equal to ax. So this lambda x here is ax, so that gives us a to the kx. And then we get a to the k minus 1 times x is lambda to the minus 1, lambda to the k minus 1 x. So again, we can replace that there. So that gives us a to the kx equals lambda to the kx. So that was assuming it was true for n equals k minus 1, then we prove that it's also true for k. So therefore it's true by the principle of mathematical induction. And that concludes the solutions for question number 7.